Hybrid Cloud Kopi Hour. Today we'll be bringing you some really cool content from our Managed Cloud Services team, the APAC Managed OpenShift Black Belts. Internally, we refer to them as an acronym, of course, for their name, MOBB, or the MOBs. The MOBs work closely with our managed OpenShift customers and field teams supporting real-world installs of ROSA, ARO, and more. They get to play in this space every day and see all the ways that a managed OpenShift service is proving helpful to our customers to reach their goals. And with this experience, they have gained a massive amount of knowledge on how to do real-world deployments the right way. So today, I'm excited to share with you their recent session on scaling and high availability in ROSA and ARO. And as an added bonus, both our presenters are standing by live in the chat to answer your questions and share their stories and experiences. Be sure to say hi. So today we're featuring two mobs. First up is Nethali to cover scaling in OpenShift. Nethali dives into scaling, different types of scaling, resource management, and more. You're going to learn concepts and stuff about how it works, sections on optimizing, and best practices. After that is Suresh to present on high availability, and he's going to deep dive into everything, from application probes to load balancing capabilities and controlling pod placement, everything to make your clusters safe. And you won't want to miss the best practices session where Suresh gives you the rock solid foundation to making your OpenShift cluster always available. So we really think you'll find this session interesting and have come ready with your questions as, again, Nethali and Suresh are going to be standing by live for Q&A in the chat. Engage with them, ask them your questions, and enjoy the session. Thanks.
Hello everybody. Today we are going to talk about scaling in Red Hat OpenShift. We will cover types of scaling, key concepts, how auto-scaling works, optimizing auto-scaling, and best practices. Let's see what are the types of scaling. Scaling refers to the ability of OpenShift to automatically adjust the number of running instances of application based on demands. This can be achieved manually or automatically. When it comes to manual scaling, to instantly change the number of replicas, administrator can use the OSI scale command to alter the size of job, deployment, or replication controllers, etc. When it comes to auto scaling, there are three types of auto scaling: horizontal scaling, vertical scaling, and cluster scaling. Horizontal scaling. Horizontal scaling involves altering the number of pods available to the cluster to suit the change in workload demands. You call scale in when you reduce the number of pods, and you call scale out when you increase the number of pods. Vertical scaling. A vertical scaling mechanism involves the dynamic provisioning of resources such as RAM or CPU of a cluster nodes to match the application requirements. This is essentially achieved by tweaking the pod resources based on the workload consumption. This scaling technique automatically adjusts the pod resources based on the usage over time, thereby minimizing resource wastage and facilitating optimum cluster resource utilization. Vertical pod autoscaling works best with long-running homogeneous workloads such as databases. It has few limitations also. For example, vertical pod autoscaling is not ready to use with JVM-based workloads due to limited visibility into actual memory usage of the workload. Other than horizontal scaling and vertical scaling, we have even a multi-dimensional scaling. It combines horizontal and vertical scaling simultaneously. This is less frequent and not recommended. More complex to manage because defining when to scale horizontally or vertically depends on many parameters, which are sometimes hard to predict. The third type is cluster scaling. Cluster scaling involves increasing or reducing the number of nodes in the cluster based on the node utilization matrices and the existence of pending pods. The cluster's autoscaling typically interfaces with the chosen cloud provider, but in the case of OpenShift Container Platform implementation, Cluster autoscaling is integrated with the machine API by extending the compute machine set API. What this really means? As you can see on the screen, OpenStack has custom resources called machine pools, machine sets, and machines specifically in AWS infrastructure. You can consider machine set and machines similar to replica set and replicas or pods. You can change the number of replicas in the replica set to change the pods. Similarly, you can change the replicas of machine set to change number of machines which is controlled by machine set. But when it comes to AWS, you have another high level abstract called machine pool, which basically control even machine sets. Actually, machine set, a single machine set is always available in one availability zone in AWS. So we are not going to go more detail, but this is a very high level explanation about machine pool, machine set, and machines. What will happen is basically cluster autoscaler call machine pool, which call the machine set, and eventually it will create the machines. Note that horizontal, vertical, and cluster autoscaling are unrelated to each other. They are developed in separate projects and can be used independently from each other. Therefore, the cluster requires fine-tuning the settings of autoscalers so that your work is running correctly. OpenShift has been already fine-tuned and it's ready to go. So let's try to understand some key concepts under the hood of scaling. The first one is resource requests and limits. How much of resources a container need can be optionally specified using resource requests and limits. So what is resource request? When the resource request is specified for a container, the kube scheduler uses this information to decide on which node the pod is placed. It is used for scheduling and to indicate that a pod cannot run with less than the specified amount of compute resources. The kubelet reserves at least the request amount of resources specifically for that container. If the node where the pod is running has enough of resources available, it is possible and even allowed for a container to use more resources than its requested resources. Then what is resource limit? When a resource limit is specified for a container, the kubelet and container runtime enforce those limits so that the running container is not allowed to use more of the resources than the limit. This is used to prevent a pod from using up all compute resources from a node. In some cases, kubelet even reserve the limit which is greater than or equal requested. Because of the reservation, the scheduler refuses to place a pod on a node although actual memory or CPU resource usage on node is very low since the capacity check fails. This protects against the resource shortage of node when resource usage later increases for the peak request rate. The second concept, the resource allocation in the worker node. In Kubernetes, worker node memory and CPU are divided into 4 categories: allocatable, kube reserved, system reserved, and eviction threshold. What is allocatable? Actually, the allocatable is the resources available to your pods. Kube reserved. The kube reserved resource necessary to run Kubernetes agents such as kubelet, the container runtime, etc. The system reserved. As its name says, this is the resources needed to run the operation system and system daemons. And last, eviction threshold. Memory pressure at the node level to the system is sometimes lead to what we call arms, out of memories. This affects the entire node and all pod running on it. node can go offline temporarily until memory has been reclaimed. To avoid or reduce this probability of system arms or system out of memories, Kubernetes reserved some memory via a specific flag called eviction hard. The Kubernetes attempt to evict pods whenever memory available on the node drop below the reserved value. For this reason, resources reserved for eviction are not available for pods. You need to account all of them. If your cluster runs extra stuff, something like daemon set, CNIs like funnel or log collectors such as fluentd, it will further reduce the resources available for your pod or allocatable resources. There is a very nice resources that you can go to this URL and you can check the resources based on different node types. So I will leave it to you and let's go to the next section. How auto scaling works. Let's have some understanding how horizontal pod auto scaling works. The first step, the pod CPU and memory usage is pulled by kubelet every 10 seconds. So after that, the matrix server will aggregate matrices and expose them to the rest of the Kubernetes API in every 60 seconds. Following that, the horizontal pod autoscaler controller, the controller of the horizontal pod autoscaler is in charge of checking the matrices and deciding to scale up or down your replicas. By default, the HPA check pods matrices every 15 seconds. In the worst case scenario, the horizontal pod autoscaler can take up to 1.5 minutes to trigger the autoscaling. You can see you can add these 10 seconds, 60 seconds plus 15 seconds, roughly around 1.5. Okay, let's think. Now horizontal pod autoscaler want to create another pod, but your node does not have resources. In that case, the cluster autoscaler comes into the picture. Because you have to create another node. The cluster autoscaler has a reaction time of 10 seconds. The cluster autoscaler checks for unschedulable pods in the cluster every 10 seconds. Once one or more pods are detected, it will run an algorithm to decide how many nodes are necessary to deploy all pending pods and what type of nodes group should be created. The entire process takes no more than 60 seconds on a cluster with less than 100 nodes. The average latency should be about 5 seconds. And if your cluster has nodes around 100 to 1000 nodes, it is said that this time takes no more than 60 seconds. Now let's imagine that our cluster has less than 100 nodes, so this becomes 30 seconds. Okay, next step is node provisioning. Node provisioning actually depends mainly on the cloud provider, but it's pretty standard for new compute resource to be provisioned in 3 to 5 minutes. So let's say it takes 3 to 5 minutes. And last, the pod creation time. Launching a container generally happens in a couple of milliseconds, but some application may take time to boot depending on the kind of application. For example, JVM based, it takes some time, and also some operation to perform. For example, some data injection might take time. More importantly, downloading the container image could take from a couple of seconds up to minutes depending on the size of and number of layers of the image. So that's how horizontal pod autoscaling work and all the time involving in each and every steps. So with that explanation, we have a good understanding that pod autoscaling lead time is as shown on the picture. With the default timing, horizontal pod autoscaler reaction time 10 seconds for pod CPU and memory scrap, 60 seconds for matrix server aggregation, and 15 seconds for HPA check pod matrices. And if you want to create another new node, the cluster autoscaler reaction time comes with a 10 second plus 6 additional 30 seconds. and node provisioning time take around 3 to 5 minutes, and pod creation time also add to that. Okay, that's how, and that's the pod auto scaling lead time. So how do we optimize auto scaling? Let's have another look. If you add all these times, it will take around 6 to 7 minutes for entire process. Are you happy to wait for 6-7 minutes to handle sudden surge in demand? No, right? So in that case, we have to see how to optimize this auto scaling. As you can see from top to bottom, OpenShift use kube controller manage flags for optimal HPA performance. So these flags have been already optimized. They are fixed and you have no control on this. So therefore, you have no control on this HPA performance. You cannot reduce the time. And also OpenShift cluster autoscaler reaction time is 10 seconds. So in that case, you have no control on that also. But node provisioning time and pod creation time, of course, you have no control. You cannot reduce node provisioning time. You cannot reduce the pod image downloading time. But you can have some workaround to optimize them. So let's have a look. The first one is node provisioning time. You can have some workaround to minimize new node creation. You can optimize HPA target threshold value. You can create node proactively in advance. In terms of pod creation time, you can cache the image in advance. So let's little bit dig deeper and see how we can do each and every steps. First one, node provisioning time. So if we don't have a control on node provisioning time, how we can optimize this timing? The one step is minimize new node creation. Try to minimize new node creation. Minimize creation of new nodes if possible. Choosing the right instance type for your cluster has dramatic consequences in your scaling strategy. For example, if your node has space only for few pods, as you can see on the left side, you have to provision in a new nodes for additional replicas, incurring additional another 6-7 minutes delay. The lead time to trigger the horizontal pod autoscaler, cluster autoscaler, and provisioning of the compute resources on the cloud provider. But if your node has a space for a large number of pods, as you can see on the right side, this will reduce it dramatically because you have enough space always. Choosing a large instance type also has another benefit. The ratio between the resource reserved for kubelet, operating system, and eviction thresholds, what we discussed earlier, and the available resources for your pods, the ratio is greater. Select the right instance, but not the biggest instance at all the times. You have to have some kind of a research and try to select the optimum large enough node size. There is a peak in efficiency dictated by how many pods you can have on the node. Cloud provider limit the number of pods. Sometimes it's dictated by the underlying network on per instance basis. You have to consider all of this. You should also consider if you have only few nodes, the impact of failing one node is very high. The second workaround that you may try is optimize HPA target threshold value. At the high level, HPA keep an eye on resource request matrices coming from your application workload, nothing but pods. By querying the matrix server, it compares the target threshold value that you set in the HPA definition with the average resource utilization observed in your application workload, that is CPU and memory. If the target threshold is reached, the HPA will scale up your application. In this example, your target is 50%. if your CPU or memory, according to your definition, if your CPU or memory, either or both of them, is greater than 50, your HPA will scale up your application. So after some research, this target threshold value may be set low enough so that existing pods can handle the growing traffic until a new node is created to have space for pods. So that's another workaround that you can try. And the third one is create a node proactively in advance. So if you can afford to have a spare node available at all times, teach the autoscaler always to have a spare empty node. You may create a node and leave it empty. As soon as there is a pod in the empty node, you create another empty node. But cluster autoscaler doesn't have this functionality built in, but we can have a nice workaround for this. So let's see how it works. Run a low priority deployment with enough requests to reserve an entire node, as you can see on this picture. As you can see on the right side, there is a low priority placeholder pod which always reserved a spare node. Consider this low priority pod as a placeholder, and as soon as a real pod need the resource, you could evict the placeholder pod and deploy the real high priority pod. Let's see how it works. So the new application pod comes, it evicts the placeholder pod, and now what happens is there's a no node for the placeholder pod. It will create another new spare node and your low priority placeholder pod will appear there. So pay extra attention to the memory and CPU requests so that they are used to reserve the space of your new spare node. You may provision a single large pod that has roughly the request matching the available node resources. To make sure that the pod is evicted as soon as a real pod, which is the application pod, is created, you can use pod priorities. Pod priority indicates the importance of the pod relative to other pods. When a pod cannot be scheduled, the scheduler tries to evict the low priority pods to schedule the pending pods. You can configure pod priorities in your cluster with a pod priority class. So this is the third option that you can try, and we are proposing this one. There are some workaround that you can optimize node provisioning timing. And the next one is pod creation time. If your company allows to cache the image in advance, in that case, always try to cache the image in advance. There are some companies which has an image pool policy set as always for some reason, for example security. In that case, you have no chance for this because it always has to pull the image from the registry. But if your company allows, use pod creation time. You can optimize pod creation time by downloading the image in advance. There are some mechanisms you can use to cache the image into the node in advance. For example, image puller. Use daemon set. So this use the daemon set to download images in each and every node. And also there are some operators, as you can see in the Kubernetes image puller, kubefledge, etc. And also even you can use the placeholder pod in the spare node to download the image in advance. You may use the application image, if supported, as a low priority placeholder pod when creating the spare node. This will pull the image into the spare node in advance and allow the real pod to start faster, replacing the low priority pod. Although these practices may reduce the pod creation time, we highly recommend to experiment them to suit your requirements. Last but not least, double check the image pool policy in your organization. And the next step is, let's go and try to understand what are the best practices in scaling. The first one, use the latest version of autoscaler object. Kubernetes is a high velocity platform. So there are a lot of things happening. With every new releases, performance and compatibility of different Kubernetes version with the autoscaler releases are truly tested and documented. It's highly recommended to use only the compatible autoscaling object of the Kubernetes control plane version to ensure the cluster autoscaler appropriately simulates the Kubernetes scheduler. The second one is be specific on resource requests and limits. It is crucial to ensure the pod resource requests are comparable to their actual consumption. As a recommended best practice, cluster administrator leverage historical consumption statistics and ensure each pod is allowed to request resources close to the actual trend of usage. So there are many ways that you can define requests and limits. The first one is defining the request lower than the actual usage. So in this case, it is sometimes problematic since your nodes will be often overcommitted. Overcommitting nodes can lead to the excessive eviction, more work for kubelet, and a lot of rescheduling. So it's not a good practice, maybe. And the second option is you can set the request and limit to the same value. In Kubernetes, this is often referred to as a guaranteed quality of service class and refer to the fact that it is importable, that the pod will be terminated and evicted. The Kubernetes scheduler will reserve the entire CPU and memory for the pod on the assigned nodes. Pods with guaranteed quality of service are stable but also inefficient. For example, if your app uses 256 megabytes of memory on average, but you reserve 2 gigabytes, we have 1.5 gigabyte unused most of the times. So we have to ask the question, is it worthy? If you want to have an extra stability, yes, it's worthy. Use guaranteed quality of service, which means request equal to the limit when you want to have a minimized rescheduling and eviction for your pods. And last option is, if you want to have the efficiency, you might want to lower the request and leave the gap between the request and limit. This is one of the practice that you can increase the efficiency. When your requests match the actual usage, the scheduler will pack your pods in your node efficiently. Use this mechanism, which is request match to the actual average usage, when you want to optimize your cluster and use the resources wisely. For example, you can use this kind of a mechanism for web application, REST API application, etc. And the next option is, in terms of best practices, define resource request and limits for each pod. I am repeating it, for each pod. The fact is, the autoscaler relies on each node utilization and pod scheduling status to tackle the scaling changes. Calculating node utilization relies on the simple formula dividing the sum of all resources requested by capacity of nodes. As a result, missing resources requests for one or many pods affect the calculation of node utilization. It is recommended practice to ensure all pods running with a node have resource request and limit defined for optimal scaling at any given time. The fourth point is group node instance with similar capacity. A cluster autoscaler works with the assumption that every node of the node group has the same memory and CPU resources. To achieve this, a template node is created by the autoscaler on which all cluster-wide scaling operations are performed. To ensure the autoscaler create the template node perform accurately, it is ideal to have node groups with the nodes having the same resource and footprints. And the fifth point is specify disruption budget for all pods. Kubernetes support defining the pod disruption budget as a cluster object for voluntary or involuntary disruption of workload replicas to prevent incurring losses. Cluster administrators should define pod disruption budgets to ensure the autoscaler maintain a maximum threshold of pod for optimum functioning of cluster services while preventing budget overrun. In this session, we already covered type of scaling, key concepts, how autoscaling works, optimization of autoscaling, and best practices. Thank you very much.
Hello everyone. Today we will talk about how to achieve high availability of application when deployed on OpenShift clusters. We will cover how high availability can be achieved with the help of application probes, load balancing techniques, scheduling strategies, pod disruption budget, pod priority and preemption, and then we will discuss some of the best practices to be followed to achieve high availability. When we talk about high availability, it's important to consider cluster high availability along with application high availability. Though we will be focusing on application high availability today, when deploying ROSA ARO OSD clusters, always ensure the clusters are deployed in multiple availability zones. Also, when you scale the cluster nodes, ensure to scale the nodes evenly across availability zones. Now, to improve reliability and availability of applications, we use application probes. Let's take a look on how application probes helps in achieving high availability. OpenShift includes two types of probes for evaluating the status of applications. A liveness probe examines whether an application is functioning properly and if not, causes it to be restarted. A readiness probe examines whether an application is ready to receive traffic and if not, causes it to be removed from the service endpoint list. There are three types of application probes: HTTP GATE, TCP socket, and exec. They are all slightly different in how they probe the pods and containers. The HTTP GATE probe makes a simple HTTP or HTTPS connection. If the response code is between 200 and 399, the check is deemed successful. The TCP socket probe makes a pure socket connection to the identified port and is only considered successful if the connection can complete. Neither HTTP GATE nor TCP socket require anything special of the pods or containers being probed. The most powerful probe is exec. This probe actually results in the specified executable being run inside the designated pods container. If the exit code of the executable is 0, the probe is considered successful. The reason that this probe is so powerful is that any executable inside the specified container may be run. This could be a custom program that checks not only the process running in the specified container, but that checks other things in or even outside of OpenShift environment to determine whether to pass or fail is warranted. The liveness probe determines whether or not a pod is alive and healthy. If liveness probe fails, OpenShift will terminate the pod and then restart it with an exponential backoff delay. Whereas readiness probes determine if a pod is able to receive traffic. It is possible that certain application instances may not be dead or require restart, but may also not be in a state where additional traffic should be sent to them. As an example, an application that has hit its CPU threshold or for some of the other reason cannot handle an additional load may still be working fine, but sending new load to it may cause service disruptions. If a readiness probe fails a sufficient number of times, this pod is marked as not ready and this causes it to be removed from the endpoint list for a service that would map to it. In this way, additional traffic going to the service is no longer balanced across pods that are not ready. Once the pod passes the readiness checks again, it is marked ready, and this results in the pod being re-added to the endpoint list. Then the traffic will again distribute it to the pod. Now there are some other important settings when configuring these application probes. Initial delay seconds, which is how long to wait after the pod is launched to begin checking. Timeout seconds is how long to wait for a successful connection. It could be HTTP gate or a TCP socket only. Period seconds, how frequently to recheck for the connection. And failure threshold, which states how many consecutive failed checks before the probe is considered failed. Now let's take a look at load balancing capabilities which we have. OpenShift provides built-in load balancing capabilities which can distribute the traffic across multiple replicas of your application. This helps to ensure that no single replica is overloaded and that traffic can be automatically rerouted to healthy replicas if one fails. You can even split the traffic between multiple services for A/B testing, blue-green, and canary deployments. This is useful when you want to slowly onboard the newer version of the application to the users. Scheduling plays a vital role in achieving high availability of the applications. Let's take a look how we can use different scheduling strategies for this. We do not want to have all our pods on the same node because that would make having multiple pods irrelevant when nodes must be taken offline. OpenShift does a good job already at this. The scheduler by default will try to spread your pods across the nodes that can run them. Now, first of all, we can use node selectors on pods and labels on the nodes to control where the pod is scheduled. With node selectors, OpenShift schedules the pods on the nodes that contain matching labels. It's a good practice to dedicate some nodes for your mission critical applications to avoid impact, such as resource crunch on these application pods, which may be caused by some other pods running on the same node. When we want to have more granular control on the scheduling, affinity and anti-affinity rules can be used. Using these rules, you can spread the pods of a service across nodes, availability zones, or availability sets to reduce correlated failures. When latency or performance matters, pod affinity can be used, which tells the scheduler to schedule relative pods together. To avoid scheduling of some pods on the same node, pod anti-affinity can be used, which will prevent the scheduler from locating the new pod on the same node and will spread the pods across the multiple nodes or availability zones. To avoid other application pods to get scheduled on the specific nodes dedicated for your mission critical applications, tents and tolerations can be used. Tents and tolerations allows the node to control which pods should or should not be scheduled on them. Now, even after using affinity or anti-affinity rules, it does not guarantee of even spread of your replicas. With preferred mode, even spread is not guaranteed, and with strict anti-affinity mode, you may end up running single replica on nodes, which presents the problem of fault tolerance and may not be an efficient use of resources available on the nodes. This is where topology spread constraints comes into the picture. So the topology spread constraints gives you more granular controls during scheduling of the pods. You can use pod topology spread constraints to control the placement of your pods across nodes, zones, or other user-defined topology domains. By using pod topology spread constraint, you provide a fine-grained control over the distribution of pods across failure domains to help achieve high availability and more efficient resource utilization. Take a look at how a pod topology spread constraint definition looks like. Looking at this example, let's consider you want to run 7 replicas of your application across 3 availability zones. Now you can't have even distribution of 7 replicas across 3 zones. In this case, scheduler can't evenly distribute the pods across availability zones. So in that case, what it will do is it will schedule 2 pods on 2 nodes and 3 pods on the third node. This is controlled by the max queue field. The max queue field specifies the degree of imbalance in the spread. It tells the allowable difference of the number of pods between these zones. As an example, if we have max queue set to 7, the scheduler may end up scheduling the pods 700 across these 3 availability zones. The next field in this example is topology key, which is a key for one of the node label. The next field is when unsatisfiable. It is the action of the scheduler, the action the scheduler should take when it can't satisfy the conditions specified in the topology spread constraint. It could be scheduled anyway, which means even if it doesn't match the condition, the pods will still be scheduled. Or do not schedule, which means if it doesn't match the condition, do not schedule the pods. Even with all the above techniques accounted for, once a maintenance event has been completed, pods may be scheduled in an unbalanced manner. To better prepare for the next maintenance event, we may have to make sure the pods are scheduled evenly. You can also benefit from descheduler in a situation where your nodes are overutilized or underutilized. In these situations where new nodes are added to the cluster or other scheduling conditions have changed. Now let's take a look at different disruptions and how we can deal with them. Before discussing pod disruption budget, let's understand what is a disruption. Pods do not disappear until someone, a person or a controller destroys them or because of unavoidable situation occurs. Disruptions are of 2 types. Involuntary disruptions, involuntary disruptions are unavoidable, such as hardware failure, cluster admin deleting the node mistakenly, kernel panic on the nodes, or nodes running out of resources, or even a cloud provider failure. And we have a voluntary disruptions, which are typically occurred by application owner or admins, such as draining a node during maintenance activities, removing a pod from the node, typically during cluster scale down, where it removes the node from the cluster, modification to the deployment, causing a pod restart, deleting a pod, or deployment from the cluster, or application upgrades. Now, to deal with the involuntary disruptions, always ensure you have enough resources available in the cluster to run applications efficiently. Even if a node goes down for some or the other reason or application pod fails, the scheduler should be able to schedule the pods on other available nodes. For fault tolerance, always run multiple pods, at least 2 pods for your application, such that application can tolerate a single pod failure. Also, spread these pods across availability zones using scheduling techniques so that even in case of easy failure, application can still run efficiently, serving to the clients. Let's take a look at how we can deal with voluntary disruptions. As these are application owner or admin initiated disruptions, always use GitOps practices for Kubernetes manifest files. With GitOps, Git will be the source of truth even for your application manifest files. Even if someone manually modifies the Kubernetes manifest file or performs some disastrous activities such as deleting a Kubernetes resource, the files will be created again in the cluster with autosync policies. Another way to deal with these voluntary disruptions is to use deployment strategy. A deployment strategy is a way to change or upgrade an application. The aim is to make the change without any downtime in a way that usually barely notices the improvements. By default, in OpenShift, we use rolling deployment strategy. A rolling deployment slowly replaces instances of the previous version of your application with instances of a new version of the application, and it waits for the new pods to become ready via a readiness check. When using rolling strategy, you need to ensure that your application handle n-1 compatibility. The third and important way to handle voluntary disruption is to use pod disruption budget. A pod disruption budget is nothing but a budget for voluntary disruptions, which is typically used to achieve high availability of applications. This is an error budget which states no matter what, we will always have minimum set of application pods up and running all the time in case of voluntary disruption. A pod disruption budget specifies the minimum number or a percentage of replicas that must be up at a time. If you specify a pod disruption budget, OpenShift respects them when preempting pods at a best effort level. It limits the number of pods of a replicated application that are down simultaneously from voluntary disruptions. For example, if we are running 3 replicas of a pod on 2 nodes and PDB is configured to run minimum 2 pods all the time, during maintenance activity, the node running 2 pods will never be drained till the time we have an additional pod running on the second node. Now, even with all this in place, consider a disastrous situation where we don't have enough resources available to run the entire workload in the cluster. This is where pod priority can help to some extent. Let's talk about pod priority and preemption. A pod priority is defined in a priority class, which is a non-namespaced object. Pod priority indicates the importance of a pod relative to other pods and queues that the pods based on that priority. This is specifically useful when you have unknown failures like easy failures or have minimal resources available in the cluster. Pod priority ensures your pod gets the highest priority when scheduler tries to schedule the pods. The default priority is in between 0 to 2 billion. Pod preemption allows the cluster to evict or preempt lower priority pods so that higher priority pods can be scheduled or can be run if there is no available space on a suitable node. Pod priority also affects the scheduling order of pods and out of resource eviction ordering on the node. The scheduler schedules a higher priority pod sooner than the pods with lower priority if its scheduling requirements are met. You can apply pod priority and preemption by creating a priority class object and associating pods to the priority using priority class name in your pod specifications. By default in OpenShift we have 3 priority classes, and you can also have one global default priority class in the cluster, which means if the pod doesn't specify a priority class, this default priority class will be used. Now let's take a look at some of the best practices to be followed when deploying the applications on OpenShift to achieve high availability. Now, when we talk about best practices, always ensure you run multiple replicas of your application pods. You can use replica set or replication controller to ensure we have X number of replicas running all the time. Always spread your application pods evenly across nodes. You can use different scheduling strategies as we discussed to spread these application pods evenly across nodes. Then specify the disruption budget for your pods. Use PDBs so that applications will have minimum set of replicas running all the time, even during voluntary disruptions. Be aware that pod disruption budgets cannot prevent involuntary disruptions from occurring. Then define a descheduler policy. Even with all the scheduling techniques we have, once a maintenance event has been completed, pods may be scheduled in an unbalanced manner. To be better prepared for the next maintenance event, we may have to make sure pods are scheduled evenly. The next is design your application so that it can tolerate losing pods. You need to instrument your application to do any necessary cleanup when it receives a sick term. This phase has to be quick. With OpenShift, by default, you get 30 seconds when a pod gets sick term to clear all its in-flight connections. In the case of a web application, there is no time at this point to wait for the existing client sessions to be concluded. This leads us to the next principle. It shouldn't matter which pod receives a request. Because there is no way to clean in-flight sessions when a pod gets killed, it may happen that subsequent requests of an in-flight session go to a different pod after the pod that was managing the session is killed. Your application needs to be designed around this eventually. It might be okay to lose the session in some cases, but in most of the circumstances, you will want to give your customer the best user experience, which means not losing the session. For a stateless application, it shouldn't matter. However, if your server-side application maintains a state in the form of a session, then you need a way to persist it to either a cache or a database so that it can be retrieved by other pods. The most important thing is share nothing across multiple clusters. The cluster should be completely independent without sharing any resources. You might be tempted to share the storage layer or some services outside the cluster. Unless these services provide their high availability solution, the cluster should not share any service with other cluster. This way, we avoid creating a single point of failure. As an example, let's consider you have created an active OpenShift cluster wherein you are running your application in both the clusters and load balancing it via an gateway or load balancer. Now, even in case of a cluster failure or an application failure in one of the cluster, your application will still be available to your end users. Now consider a situation wherein your application is writing some data or reading some data from an Oracle database which is outside your OpenShift cluster. If you are using the same Oracle database for both of these clusters, and if your Oracle database is a single instance Oracle database, a failure in Oracle database will cause the entire application to go down. We should avoid these kind of situations. And the last is capacity considerations. Doing maintenance requires having some spare capacity at a minimum. One needs to be able to take one node of the cluster. Performing a cluster maintenance on one node at a time can take a long time for a large cluster. One can obviously take multiple nodes offline, but that requires having more spare capacity. Finding the right balance between the spare capacity reserved for maintenance and the time for the maintenance operation will take.